Why titanium?
Well, from a property standpoint, it has a really high specific strength. And what does that mean?
So specific, you just take your strength and you're dividing it by the density. So pound for pound, this thing really packs a punch.
Or in other words, it has a high strength while being really light. It also has a really nice corrosion resistance because it forms a passive film. That's an oxide layer that forms that prevents further ingress of oxygen at room temperatures. But what's also really strange about it is its history. Despite being the 9th most plentiful element and the 4th most abundant structural metal, it's rarely found in high concentrations, it's never found in a pure state, and mass production didn't start until the 1940s.
Yeah. So that's related to the name, right? This mineral has been like locked away in the earth, titanium. And so the guy who finally figured out how to unlock it from the earth, he named it after the Titans, right? Because the Titans were locked away in the earth, which I think is so cool. Now, we're going to get into that. Maybe we dive in, like, who discovered it? What was that process looking like?
Yeah, I mean, so we've known about titanium oxide or titania for a while. It's been used in pigments. It's really white. So white paint often has
if there's white paint on the wall, it's probably titania.
It's also used in sunscreen, and it's also used in food products. The white icing in Oreos actually contains a little bit of titanium
oxide. Shut up, are you for real?
Yeah.
That's wild.
Yeah, supposedly this is food grade titanium oxide, but we'll see.
Yeah, actually, for those in Europe, you may know, it's banned. They banned it 2 years ago, actually. Yeah, America, though. You can still get it.
Yeah, we're kind of behind on the food science here.
I just saw a meme, like we just had our election here, and I just saw a meme showing McDonald's fries versus US versus UK, and it's wildly different. We put so much garbage in our food.
Yeah.
Apparently titanium. So, okay, but this was invented a while ago. Technically, they found how to like get metal, titanium, way back in 1791. This guy, I love it. I love these guys back in the old days. He's a /reverend /mineralogist /chemist. Like the guy's just doing it all. And he was in Cornwall, England, for our listeners, in the southwest of England, in the Menniken Valley. You might know where that's at. He found this black sand that's out there. And nowadays, we know that sand was ilmenite, which is just FeTiO3, so 1 to 1 to 3 there. And basically, after treating it with some acid, he technically was the first person to discover this metallic titanium. Super non-ideal way to make titanium, though.
Yeah, and he names it meconite.
Yeah, because it was the Menniken Valley. It was named after like the location. Pretty cool name, I think, though.
Mm-hmm. It was really just a few years later, 1795, that we get the name that we're more familiar with. This is a Berlin chemist, Martin Heinrich Klaproth. He independently from Gregor isolates titanium from a Hungarian mineral known as rutile.
Yeah, that's TiO2.
Mm-hmm.
So the first guy was FeTiO3. This is now TiO2 as the starting material.
So he starts with the oxide. And just like you had mentioned, because it's entrenched deep in the earth like the Greek Titans, he calls it titanium. But even then, most of the time, this wasn't very pure. And for a really long time, that was really the main method. There wasn't a lot of progress in terms of purifying it. But in the 1880s, there were 2 Swedish scientists who successfully produced 94% pure titanium. This was Lars Fredrik Nilsson and Sven Otto Pettersson. They got it to about 94% pure. And interestingly, Nilsson also discovered scandium.
That's wild. That's not even that long ago. 140 years ago. Yeah. That's wild. Okay, so they're making it better. And then it was Matthew Albert Hunter at Rensselaer Polytechnic Institute in the United States. He figures out how to isolate it through something closer to what we do nowadays. He's now starting with titanium tetrachloride as the precursor, and he's adding to that sodium. So there's an exchange reaction in a steel bomb, right? The sodium wants to form sodium chloride, so it's going to strip away the chlorine, leaving behind the metallic sodium, or the metallic titanium. So that's a step better.
And apparently it was pretty dangerous too, as these thermodynamic reactions go. So much so that he actually did most of his experiments at the Rensselaer Polytechnic Institute's football field.
For real.
Like he would just go out there and like run away and set that thing off and let it go because it's open space. There's hopefully no one around. I don't know if the University of Utah would let us. I want to get away with that, but I say Rice-Cycle Stadium, they let me sneak over there. That's wild, do our blacksmithing. So a couple years later, then we finally come to today's process, right? When you go about, if you look up on the Wikipedia page for making titanium, it's the Kroll process, right? Named after Wilhelm Justin Kroll. This is a guy from Luxembourg, and he did a slight variation on what Hunter did. The year's now 1932, and he realizes if you take this titanium chloride, and instead of adding sodium, first he tried it with calcium, and eventually he tried it with magnesium, and it just works really well. The magnesium does the same thing as the sodium did. It wants the chlorine, so it pulls it away, leaving behind metallic titanium. What I think is wild is that today, they still do this in a batch process. We don't have a continuous process for making titanium. How crazy is that? Yeah, and that's what makes it so expensive too. despite it having really good properties, because of the lack of a really well optimized process flow, it ends up just being, pound for pound, much more expensive than the alternatives.
Well, Kroll's an interesting character too. He's one of these guys who flees Europe during the war, and to our benefit, he comes to the United States, joins the institute, like the Bureau of Mines, I think,
Bureau of Mines,
and starts cranking out titanium.
Yeah. And so as early as 1944, the Bureau of Mines was making about 15-pound batches, so they could eventually make about 100 pounds of titanium a week. But that wasn't enough.
And what was the interest? Like, what are they? Because, okay, it's one thing from a scientific perspective. You got a new metal, but what are you doing with it?
Well, at this time, right, this is about towards the end of World War II. There's desire to improve our aviation capability. And with aviation, it's all about being lightweight and strong.
We saw that in the war. Like, the Pacific is massive, and we were really limited on the military targets we could hit by how far you had to fly. Now, if you can make a lighter airplane, Jared's going to jump in and tell us all about this. I'm sure he's the aerospace guy, but lighter airplanes mean longer missions, more capabilities, and titanium with its high specific strength, that could be just what we need.
At the same time, the Soviet Union was also very invested in titanium, and we'll get a little bit into their supplies. And so there was impetus for the U.S. to invest in this material. And in 1948, the DuPont company was the first to start producing titanium commercially.
Not just chemicals, metals too. That's awesome.
And those first batches of titanium went to being used on experimental military jets such as the F-84 and the F-86. And in fact, to try to kickstart the industry, the U.S. government, specifically through the military, funded tons of projects, encouraging the manufacturers to substitute steel with titanium wherever possible. Going so far, the Army Ordnance Corporation basically placed an order outset for $1 million worth of titanium metal to try to spur industry.
If you can make it, we'll buy it from you, basically.
Yeah, one of the earliest uses of titanium that I know of, talking about the planes, is Lockheed Martin. When they were building the F-104 Starfighter, for the exhaust nozzles on the jet, they had to use titanium because it burned so hot that it was like the only material that would really hold up to it. And I think at the time, from the book that we reference in the Radar Absorbed Materials episode, which is called Skunk Works by Ben Rich, he kind of talks about how when they pitched the idea of titanium, it was considered like a really rare metal that wasn't often used. And this would be early 50s, around, I think maybe 1951 for the F-106.
The sweet looking plane, dude.
Oh, yeah.
Starfighter. That's rad.
And incredible name.
Oh, yeah.
That's pretty rad.
A little better than a lot of these just sort of acronym things. And yeah, that really signals kind of this change. In about 1951, the Materials Advisory Board projected the need for 30,000 tons of titanium products. But actual shipments were only 75 tons at that time, barely enough for research applications.
And I see a problem coming because if it's coming from rutile minerals, the Rutile Mountains, that's in Russia. This is during Cold War. They're wanting to do the same things we are. Was this a sort of supply and demand dispute where we're wanting the mineral that they don't want to share with us at this time?
Well, it really came to head when we were building the A-12 and the SR-71, which are Mach 3 planes, and so they needed titanium. And so what ended up happening was, this was through the CIA and their black budget projects. They actually created a bunch of shell companies, and those shell companies bought titaniums in different amounts.
Oh, what? So they didn't know it was like the U.S. military buying it?
Yeah, and they brought them all here and then did it here.
Brilliant.
Right, so they sold us the materials to build the plane to spy on them.
Yeah, and then another thing they kind of talk about is once they actually got the titanium, there wasn't a lot of companies that would make these titanium plates. There's actually one company that would mill titanium, and when you'd actually get these like milled plates, the quality was questionable. Sometimes it was really good, and sometimes it was just awful.
Dude, it's a new material. They don't know how to do it yet.
Yeah, from what I was reading, most of the processes we had for steel wouldn't work on titanium. The same parameters for doing things like milling or processing, temperature controls, heating treatments just didn't work.
Even worse, because for planes, the things they're using, a lot of it was also for aluminum. So they had these tools meant for aluminum, an incredibly soft material. And
that's right. Yeah, they were breaking bits all the time. They had to go and not only change their parameters, but also design new steels and milling tools.
They talked about when it came time to really start putting these together, that they actually created like basically a school, like a class where they would teach, this is how you mill titanium. This is what you should do. And I don't remember the number ended up being, but they estimated they saved a lot of money by just teaching people the proper techniques and giving them the proper tools.
And it wasn't just learning how to process it. The U.S. Government, the military, was actually a key player in developing what's currently the most popular titanium alloy, Ti-6-4 or titanium, 6 aluminum, 4 vanadium.
That's like the only one people have ever heard of, Ti-6-4.
It's used in about 50% of the applications.
Okay, yep.
And it really was the military's push to get something that was a good all-arounder, that could be processed easily and had a good balance of properties. And the U.S. gets a lot of focus here because the government basically kickstarted the industry and like carried it to what it is now. But the Soviets also put a lot of effort in. By the 1980s, the USSR, like you mentioned, was roughly 70% of the global output, more than 5 times the production capacity of the US. And they were using it too. They were really interested in using it in constructing submarines. They built about 9 to 10 ships by the end of the 1980s. And the key advantage here was that they had a lower magnetic signature, so it was harder to detect them.
I can't imagine that like the specific strength is the key thing, but it's magnetic signature, so for detection.
It could also dive to greater depths.
Cool.
And so, the U.S. was very worried about this because most of their technology was for combating submarines on a similar level. And so they thought, do we need to make our own titanium submarine? And ultimately, they just designed a torpedo that could go after it.
Okay.
So that ended up being the better solution. So the submarines, they built a lot of those were the Lyra class, and they built one, this so-called Papa class submarine, which could operate far below, any of the contemporary NATO counterparts. But it cost a lot of money to make. Even though they had a lot of titanium, the processing was still expensive. The maintenance was still expensive. Just to build the prototype cost 1% of the Soviet Union's entire 1968 GDP.
Dude, but it looks pretty cool. I'm looking at it right now. That's a cool sub. 1% of your GDP for a single vessel. That's
insane.
Wild. Absolutely wild.